entering through the same point, but starting at a different time in the cycle of the plate. Notice that its path line crosses that of the first element almost at right angles, and it leaves around the other side of the plate. Now you see elements marked at both times in the cycle of the plate. If we superpose the path line of the second element and compare it with a set of streak lines through the same point, you can see that none of them coincide with the second path line either. Now let's see about the streamlines. In order to find the streamlines, we need the direction of the velocity at each point. We can find this from combined time streak markers, such as you see here. If we take a transparency of one frame of the multiple time streak lines and overlay on it another transparency taken a few moments later, we can connect the endpoints of the streak lines and show the particle paths for short time intervals. Here you see the short dashes made by connecting the endpoints of the time streak lines. They show us the velocity direction at each point. If we draw lines parallel to them, these are the streamlines. The total streamline picture you see here is for the same instant that the first particle we observed with a path line entered the frame. The dotted streamline is the one that passes through the same point. If we compare the dotted streamline with the path line through the same point and at the same instant in time, you see they are quite different. If we compare the dotted streamline with a set of streak lines entering through the same point, they do not coincide either. In a transient flow, the streak line, the path line, and the streamline are all different. If the streak lines move sidewise, as you see here, then the flow is transient, and we cannot use the streak lines for streamlines. In a transient flow, we must work out the velocity field from some kind of combined time streak markers. We've seen one way to make the flow visible. Now let's see how to use this information to solve engineering problems and as a basis for mathematical analysis. As an example, let's consider straight-wall diffusers. As you probably know, a diffuser is any passage that decelerates the flow and causes a rise in pressure. In subsonic flow, the diffuser is merely a diverging passage. Between 1900 and about 1950, a number of studies showed that if we increase the divergence angle of the diffuser 2 theta, that the pressure rise is increased up to some modest angle. But further increases in angle cause the pressure rise to decrease. At that time, we still did not have, however, any good picture of the overall flow patterns, nor did we have good methods for predicting optimum performance. We then began a series of systematic visual studies, and these quickly led to better understanding and to improve predictive methods. The bubble technique can show us what these patterns actually are. Let's start with the walls parallel. Notice how the velocity drops sharply near the wall, and in this region the particles slide evenly over each other. This low velocity region is called a laminar boundary layer. Now let's open up the diffuser to a total angle of about 7 degrees. The increasing area of the passage causes the velocity to decrease and the pressure to rise in the direction of flow. Watch a streak square in the middle of the passage. You can see the deceleration. Also notice the flow near the wall. You see a thicker boundary layer now, and it is no longer steady. Instead, you see irregular, time-dependent eddies. This kind of boundary layer is called turbulent. Even though some of the particles very near the wall do not have enough momentum to overcome the rising pressure, they mix with the particles farther from the wall and are given sufficient momentum to keep moving in the downstream direction. If we increase the divergence angle of the diffuser further, something new occurs. Slow-moving particles begin to accumulate near one wall and then move upstream, forming what we call a stall. The mainstream is forced to separate from the wall and move around the stall. The pressure change caused by the movement of the mainstream is enough so that after a short time the stall washes out again. The whole cycle of stall buildup and washout then repeats in time. These unsteady motions we call large transitory stall. In this regime, the whole passage acts like an oscillator, even though the upstream flow is steady and symmetric. If we increase the divergence angle of the diffuser still further, the stall forms a relatively steady recirculating region on one wall. The mainstream separates very near the throat and hugs the other wall. If we move the mainstream to the opposite wall, it stays there. The pattern is what we call bistable. Usually we refer to this pattern as fully developed stall. If we increase the diffuser angle to high values, the flow separates from both walls. We observe a jet flow pattern. In studying fluid patterns, it's important to examine the whole flow field. Here's a diffuser with a lower divergence angle. A bubble wire near the surface of the flow shows an entirely unstalled flow pattern. But now we'll turn off this wire near the surface and turn on another one deep in the flow near the floor of the channel. This wire shows us that one corner of the flow contains a large stalled area. The wire near the surface still shows unstalled flow. If we'd used this wire alone, it would seriously have misled us about the nature of the flow pattern. Like any other experimental tool, flow visualization must be used with care to obtain reliable results. Knowledge about flow patterns is most useful when it's summarized in the form of a correlation. In the case of our diffuser problem, we can show the summary by this chart. It shows divergence angle 2 theta plotted versus length to width ratio, the length of the diffuser divided by the width, N over W. The chart shows us when we will find each of the 4 flow regimes you've seen in terms of the parameters. These lines indicate shifts from one flow regime to another. One point that needs emphasis about these shifts in flow regime is that it's very seldom that we can predict them on theoretical grounds alone. Even when we have a good flow model and a sound theory based on it, within a given regime we may not be able to predict where that regime ends. This is the case in the lowest region. In this region, if we stay well below the line of first stall, then we can use Prandtl's potential theory boundary